Why do you think you need to know that something is a car in order to avoid hitting it? We want to have an approach which works universally.
Welcome to Talking Autonomy. I'm joined today by Volkmar Uhlig, our CTO and co-founder at Ghost. We talked in earlier episodes about the challenges of image-based AI and how fundamentally it's impossible to train the long tail. And so there's always this risk of misrecognition or not being able to reason about everything that might be on the road. And so in the early days, Ghost decided that they wanted to take a very different approach towards the AI algorithms behind our technology. And that caused Volkmar and the team to come up with an approach for universal physics-based AI. So in this episode, we're going to dive into that technology, how it works, and ultimately how it delivers safety. So Volkmar, take us back to the beginning. One day you were staring out the window thinking about how we might see things from the car. How did you happen upon this idea of physics-based AI?
When we try to understand the world and you look out the window, there is so much variability. And object recognition is almost impossible, because even if I would ask you, can you tell me all the things we need to learn? And can you just write them down, and then we can go through that and do that? It's impossible to make that list. And so as humans, we are abstracting the world in known objects and object categories. And this is kind of, I think, where the robotics world was misled, because they are starting to say, well, we need to see cars and humans and various other objects, trash cans. But all those are just proxies for what the behavior of this is. And so what we're really asking when you're driving is, how does a mass of atoms in front of me behave? Because our reaction is not to, oh, that's a human, but our reaction is to the behavior of that human. And so implicitly, we have assumptions about its velocity, its direction. Will it suddenly start moving? So a trash can, we know, will not suddenly start moving. It's kind of anchored. But a human may, or a car may. And so there are these implicit assumptions which are coming from knowing what the object is. And so now you need to know all objects and how they look like. And the way we approach this is to say, we actually ultimately care about its behavior, and that behavior can directly be observed.
Yeah, I mean, this is a kind of a foreign concept to folks. And I know as I've explained our technology to people, they often stop there and say, wait a minute, how can you not hit things or drive if you don't know something's a car versus a human? And so the whole starting idea here is that we just have to understand that there are things that we can't run into. And that gives you a pretty good set of information if you know how those things are moving and what they're doing to be able to drive. And then higher level understanding about something being a human or something else just can build on top of that.
Correct. And so that allows you then to abstract that detailed knowledge into first a core set of primitives, which say there's something present or there's nothing present. Is it moving or is it not moving? And then what's the dimension of it? How big is it, right? How tall is it? How wide is it? And then from that basis, you can then build higher level understanding of the scene if that is necessary. So in most cases, it's not. So imagine when you are sitting in a car and suddenly something comes out of a bush or so, which is completely unexpected. As a human, we are not like, oh my God, let me check if this is a cat or a ball or whatever. But we just naturally or instinctively hit the brakes.
React to it, yeah.
We just react to it, and we don't care what it is. And then you're saying, okay, now I identified it, and then I can make a more refined decision. But the immediate decision will just be the reaction to the presence of an object, independent of its type.
And this is just a fundamental part of the Ghost safety strategy, which is we want that base algorithm that can understand and sense things to be universal. So, no chance of not seeing things. We see objects, we can react to them. And then if we want to build higher level intelligence on top of that to behave differently around certain types of things, we can do that. But the first job is understand there's something there and don't hit it.
Correct, yes.
Okay, so tell us a little bit more about what this means to be physics-based. I think everybody mostly gets the idea of image-based AI, show the computer thousands or millions of pictures of what things look like, and eventually it learns. But we're not training this based on pictures of what things look like, right? So how does physics-based AI function?
Yeah. The world is made out of objects, or we are perceiving objects in the world. And we can approximate these objects as planes. So we just say, well, it's kind of boxy, and we are composing objects out of these different angled planes.
Planes are flat surfaces,
Yes,
roughly.
flat surfaces roughly, and it's good enough approximation for the human world. And so then we are training a network which is estimating the placement of these planes in space relative to us, and how these planes are related to each other. And it can be done by, do they have the same color? Do they have a contiguous gradient in space? Are they moving potentially in the same direction, or are they splitting? And so there is a couple of ways how we are clumping things together to say this forms a homogeneous region. And then we can react to those homogeneous regions.
And I can see how the training load here must be much lower, because you don't have to show a computer a million images of full cars or full objects, but just things that are representative of planes, what it might look like if the surface was in this color, in this direction, in this shape, in this size. And that can be much more universal in how it's trained.
Correct. And the nice thing here is also the data for establishing that correspondence is all present in our sensors. So we don't need to bring in human knowledge to say, oh, this is a car. We're just saying, well, there is a plane in my left camera, and can you figure out where the same plane is in the right camera, or where that plane is in the next frame? And so from those observations, we can then determine how an object is moving and where it's placed in space.
And because this approach is much more universal, it's also probably easier to train in every dimension as well as compute, right? So what are the implications on running it in the car and the processing power you need?
Yeah. So two things. One, the training set is much smaller because we need to have examples of things being placed at different distances in space. That's relatively easy to actually collect. And then it's very easy to homogenize the data set, so we know that we actually got all objects. And then the neural network doesn't need to memorize all these different patterns. It just effectively needs to figure out how to map pixels from one camera frame into the other camera frame. And that's a very simple mathematical function, which is easy to train and easy to compute. And so that means we can actually run this on not high-end graphics adapters in the car, but we can fit this into the power and computational envelope we have in hand.
Sounds amazing. So there you have it. Basically a fundamentally different approach to physics-based AI that has two macro benefits. One, a much more universal way of sensing objects, and so we don't have to worry about misrecognitions or not understanding that something's a car to be able to drive around it. And the second dimension is it just simplifies the end-to-end training and compute pipeline that really enables the scale to mass market automobiles. Volkmar, thanks for that explanation. And of course, as always, in future episodes, we'll go much deeper and explore further.
Thank you.